Okay, let's move on to section 1.3 in Anton, and this is titled Matrices and Matrix Operations. So a matrix is just a rectangular array of numbers, like so, and the way we always tell its size is by first counting the number of rows. So in this particular example, there's 2 rows, and it has 3 columns. So we say that this particular matrix is a 2 by 3 matrix. So always the number of rows is first, followed by the number of columns. Now in general notation, in case there aren't particular numbers, sometimes we'll use subscripts to denote the different positions. So A sub 2, 1, this is in row 2, column 1. It's not exactly 21, but it stands for row 2, column 1. Sometimes people put commas to separate the 2 numbers here, but I didn't. Okay, then what can we do with matrix and matrix operations? Well, we can add and subtract matrices, and that's easy. It's just done component-wise. So, for example, here are two by 3 matrices, and to add them, you just add the 1, 1 position, the term in the 1, 1 position to the term in the 1, 1 position, and that's going to be the result in the row 1, column 1 position here. Similarly, let's take, for example, the 5 and the 1, add them to get 6, and so on. So addition and subtraction is similar. Those are easy. You just do component-wise, means in each particular position, you take the sum of the terms in that particular position. Now, what's not so simple is matrix multiplication. And matrix multiplication is the most important operation. Now, before I tell you exactly how to multiply 2 matrices, let me give some motivation for why the definition is a little bit strange at first. So recall that the way we introduce matrices is through a system of linear equations. So here I have 3 equations in 3 variables, and we created a matrix by taking all the numbers that are appearing here and making an augmented matrix. Now what I did here is just take the coefficients on this side, so the 5, 3, and 6. So that's there, the 3, 1, and 1, that's our second row. I've ignored 1, 3, 7, well, I put it way out over here. Okay, and so then what I get is a 3 by 3 matrix of just the coefficients occurring on the left-hand side of the equal sign. And then what I'm going to make a new matrix of the variables, namely x, y, and z, and I'm going to list them vertically. So when I do that, I get a 3 by 1 matrix. I've got 3 rows and 1 column, and the way I want to define matrix multiplication is that here's a 3 by 3 matrix, here's a 3 by 1 matrix, and when I multiply them, I want to get this matrix here, which is just simply this equation, the first equation in the first row, the second equation in the second row, well, just the left-hand side of each such equation, and so on for the third row. And then I want this 3 by 1 matrix, you might say, well, isn't this 3 by 3 matrix? No, it's 3 by 1, because this is a single term. It looks pretty long, but this is a single term. So that's why there's only 1 column in this matrix. Okay, and so I want this to equal what's on the right here. And so this tells us a way, and 2 matrices are equal if and only if their components are equal, if each component is equal. So this tells us a way of how we should define matrix multiplication. Namely, we should take this row here and this column here and multiply the 5 and the x, the 3 and the y, and the 6 and the z, and add them together. This is similar a little bit to the dot product you might have seen. And now what I've tried to indicate here is that to multiply two matrices, you need the number of columns in the first matrix to match up or equal the number of rows in the second matrix. So here is a 3 by 3 matrix, and this is a 3 by 1, and we're only going to be allowed to multiply matrices if the number of columns of the first equals the number of rows of the second. Okay, so now let me go ahead and try to define the product or matrix multiplication, the product of two matrices. And so, okay, suppose my matrices are A and B, and I want to multiply them, and I'm going to call the answer C. So for example, A might be this matrix here. This is a 2 by 3 matrix, 2 rows, 3 columns. And B might be this matrix here, which has 3 rows and 2 columns. And so because the numbers 3 and 3 match up, I'm going to be allowed to define their multiplication. And here's the definition over here, is that the I, comma j entry, in other words, row I, column j, entry of C, the product, is you take the ith row of A and dot it, in other words, take the dot product, which I'll explain, with column j of B. So for example, the 1, 1 entry of our product C is you take row 1 of A. So let's go to row 1 of A, that's here, 2, 1, 0. And then dot it with column 1 of B. So we go to B, which is here. Column 1 is 1, 0, 1. So I've copied that down here. And what the dot product is you take 2, multiply it with 1. 2 times 1 is 2. You take 1, multiply that with 0. So that's 1 times 0, which is just 0. And then finally you take this 0 and this 1, multiply them together. And then, so now you have 3 numbers, 2, 0, and 0, and then you add them all together. And that's called the dot product of this row with this column. And so by our definition of matrix multiplication, 2 is what goes in the 1, 1 spot here. So it's a bit funny. It's not simply just 2 times 1. Although unfortunately 2 times 1 is 2 in this example, but that's not how I got this 2. And you can also see why we have this funny restriction that the number of columns of our first matrix has to equal the number of rows of our second matrix. That's so that the dot product is defined. We can multiply the 3 numbers appearing in the rows with the 3 numbers appearing in each column of the second matrix. Okay, let's do another, let's find another entry of the product. So this here is in the row 2, column 1. So that, again, always the row is listed first, then the column. So, according to the definition, what we need to do to calculate how I got this 4 here is take the row 2 of the first matrix A and dot it with column 1, the first column of B. So row 2 of A is 1, 2, 3. And then I dot it with column 1 of B. So that's 1, 0, 1. Take the dot product, which again means 1 times 1, 2 times 0, 3 times 1, and add each of those individual results together. And I do the arithmetic here and get a 4. So this is a 4. And then apparently I've calculated separately 4 and 8 is what is in the row 1, column 2 position, row 1, column 2, take the dot product, you get 4, and then this 8 comes in, this is in the 2, 2 position. So row 2, column 2, I would do 1 times 1, 2 times 2, 3 times 1. So that's 3 plus 4 plus 1, which is indeed an 8. Okay, and so that's the answer of the product of A and the product of B. Note that the answer is a 2 by 2 matrix, And in fact, that's because there's a 2 here and a 3 here. And that's going to work in general. Okay, so then let's move on to another operation, namely scalar multiplication. Scalar is just another word for number. And so if you have a number like 5 and you're multiplying it by a matrix by that scalar, it's much simpler. All you have to do is multiply each entry by that scalar. So 5 times this particular matrix, I multiplied each of the entries of the matrix by 5. So that's much easier. In fact, the only complicated operation is matrix multiplication, which is the most important operation. Here's yet another operation we can do on matrices, and that's the transpose. This is going to come up later on. So here's the definition of a transpose. Basically, the ij entry of the transpose is the j comma I entry. So I flipped the order. So it's the j comma entry of A. Let's do an example. Suppose my matrix was a 2 by 3 matrix given by this. Then the transpose is going to be a 3 by 2 matrix, 3 rows, 2 columns, and it's basically you flip the original matrix. So here is row 2, column 1, and to figure out what goes there, I flip the order, so the 2, 1 changes to 1, 2, and then I go to A and see what's in the row 1, column 2 position. Row 1, column 2, I see a 0, and so that's what the 0 here is, and so that's saying the 2, 1 entry of the transpose, denoted AT, is given by 0, so that's why there's a 0 here. And then similarly, you could figure out the other entries of this A transpose.